Good morning. Today we are going to learn Michelson-Morely experiment. This is one of the classical experiments in physics which were conducted back in 1887. At that time, the scientists thought that light, like other waves like sound waves, water waves, etc., require a material medium for its propagation. And they thought that the whole universe is filled with a hypothetical medium which is called ether. In some books you may find it as AETHER, both means the same. Now this was before even finding out that light is one of the electromagnetic wave. So since light comes from sun to earth, the scientists could not conceive the idea that it can travel in free space without any medium. So they thought the whole universe is filled with ether. Now this experiment was conducted by Michelson and Morely in order to find the relative motion of Earth with respect to ether. Michelson was very famous even at that time for his precision in measurement. His value for c, the velocity of light through free space, is considered one of the most accurate for many decades. And to conduct this experiment, he developed an apparatus which is called Michelson's Interferometer. This is a schematic diagram of the apparatus. Let us see how they conducted this experiment. Here they used a source of light S. The light which comes from this source is split into half by a half silvered plate called P1. And if the rear part of this plate is silvered, a part of the light will travel without any deviation. It will pass on straight, and a part of it will get reflected up. So there are two mirrors here, M1 and M2. The light ray which gets reflected will go up, get reflected back by M1 and can be observed through the telescope. And the light ray that goes straight will get reflected by a mirror M2 and it can be observed. It will come back and again it gets reflected down through plate P1 and can be observed the same telescope. Now these two light rays will superpose each other and through the telescope the interference pattern can be observed. This was the idea of Michelson and Morely when they conducted this experiment. Now, if there is ether, the earth is rotating in this direction. So the whole apparatus is also moving with earth with the velocity of earth's rotation, which is 3 times 10 raised to 4 meter per second. So if light have a relative velocity with respect to the earth which is moving through this ether current, they try to find a time difference between these two light rays and hence a path difference. So if there is a path difference, then there should be interference fringes. When the whole apparatus gets rotated through 90 degrees, there will be a shift in the fringes which could be observed. That was their initial idea. Let us see how much will be the path difference between these two waves. For that, let us consider the light ray which goes to mirror M2 and come back, and the light ray that goes up and come back. Here you can see another plate P2. Why is it kept there? See, the light ray which travels up to mirror M1 will pass through this plate P1 thrice. When it goes in, up, come down. So it will pass through this plate 3 times. While the light ray that get reflected by M2 will travel through P1 only once. In order to compensate for that, plate P2 is kept. So this is called the compensating plate. Now let us consider the light ray that goes in this direction. Let t be the time taken by the light ray to go towards mirror M2 and come back. So t can be equal to t1, the time taken to go towards M2, plus t2, the time taken to come back from M2 to P1. So we know that time t1 is equal to distance by the velocity. By the way, this distance is same as this distance. Let us put it as d. And this distance also is d. So here, when it goes towards mirror M2, the distance travelled d divided by, if Earth is travelling in this direction, rotating in this direction with a velocity v relative to ether, then the light travelling in the same direction will have a relative velocity c minus v. Because this is classical physics time, so at that time they thought that light also will have relative velocity with respect to the observer. So c minus v. Then we have t2, the time taken by the light to come back. So now light is traveling in a direction opposite to the rotation of Earth. So the speed is given by c plus v, that is the relative speed of light. So the total time taken t is equal to d by c minus v plus d by c plus v. So when we add these two, for that let me multiply both numerator and denominator by c plus v, and here again both numerator and denominator by c minus v. So this is equal to d times c plus d times v plus d times c minus d times v whole divided by c minus v times c plus v, which is c square minus v square. So you will get this cancel. So this is equal to 2 times dc divided by c square minus v square. So this is the time taken by the light ray to go there and come back. Now here let me take this c square common out. So time is equal to 2 dc divided by c square taken out. So this will become 1 minus v square by c square, or 1c gets cancelled. So this is equal to 2d divided by c times, okay, let me take this to the numerator. So it will be 2d divided by c times 1 minus v square by c square whole raised to minus 1. Now let me apply binomial theorem at this stage to take the power raised to minus 1. We know that by binomial theorem we have 1 minus or 1 plus d the whole square is equal to 1 plus, or let me write the common equation, 1 plus d whole raised to n is 1 plus n times d plus n into n minus 1 times 2 factorial d square plus n times n minus 1 times n minus 2 by 3 factorial d cube and so on. Okay, so here instead of d what we have is minus v square by c square, and instead of n what we have is minus 1. So if I use this binomial theorem here, the general binomial theorem for a plus b the whole raised to n is more complex, and it involves the factorial of this quantity, but we know that negative factorials are not defined in a straight way, even if it can be found by gamma function. So we will take this simplified version of the binomial theorem. So we can have t is equal to 2d by c, applying binomial here, where here d is minus v square by c square and n is minus 1. It will become 1 time plus n. So plus minus 1 times minus v square by c square. plus n is minus 1. Minus 1 times minus 1, it will become minus 2 divided by 2 factorial means 2 times 1. B square is minus v square by c square, the whole square plus etc. Now at this stage, let us consider v square by c square. V is the velocity of Earth's rotation, which is v is equal to 3 times 10 raised to 4, and c is equal to 3 times 10 raised to 8, which is the velocity of light through free space. So if you divide these two, you will get v by c as equal to 10 raised to minus 4. Now if you take the square of that, which is v square by c square, this will become 10 raised to minus 8. So this is a very small quantity. Now if you take a higher power of this, it will become this whole square again, which will be 10 raised to minus 16. So the variation will occur only at the 16th decimal place. So we may neglect the higher powers of v square by c square. So by neglecting the higher powers of v square by c square, the final expression for t becomes, let me write it here, t is equal to 2d by c times 1 plus minus 1 times minus v square by c square. So it is 1 plus v square by c square. So this is the expression for time taken for the light beam to go towards mirror M2 and come back. So let me keep this equation here. I will need it to compare with the time taken by the light ray to go up to mirror M1 and come back. So let me keep it here, and I hope you understand this derivation. If you have any doubt, later you can ask. So let me derive similarly an expression for time taken for the light ray to go up to mirror M1 and come back. See, the whole apparatus is rotating with Earth. So when the light ray starts from this plate P1, the whole apparatus which is rotating with Earth must have moved in the same direction. So I have shown here with dotted lines the position of mirror M1 and M2 at a later time. When the light has gone up, the mirror M1 will not be here. It would have moved to this position, and by the time light comes down, this plate P1 also must have moved to another position, which is shown by this dotted line. And what is traveling here is light, so you can keep the velocity of light. Now to find that time, let us put it as t prime, the time taken by light ray to go up and come down. So this is equal to t1 prime, light's time to go up, plus p2 prime, which is the time taken by light to come down. So the total time will be t prime. So by symmetry, we can say that both the time taken to go up will be equal to the time taken to come down. So this is equal to twice t1 prime. Both are same. So I am writing it as twice t1 prime, and I will find that expression for t1 prime. So we have the time taken for the light to go up and come down. For that, let me consider this triangle P1, B prime, C. See, this is a right triangle. So I can use Pythagoras Theorem for this right triangle. So applying Pythagoras Theorem, I can put it as from triangle P1, B prime, C. We have P1, B prime, which is the hypotenuse, whole square is equal to base square plus height square. Base is P1C, the whole square, plus height is CB prime, the whole square. So let me substitute this value. This is the distance traveled by light with a velocity c in time t1 prime. So I can put it as distance traveled is time times velocity. So c t1 prime, the whole square, is equal to P1c is the distance travelled by the apparatus along with Earth in time t1 prime. So it's travelling with a velocity v. So I can put it as v t1 prime, the whole square, plus cb prime is the same distance. So d square. So our idea is to find t1 prime. So let me put the terms having t1 prime to one side. So this is c square t1 prime square minus v square t1 prime square is equal to d square. Or taking t1 prime square outside, t1 prime square times c square minus v square is equal to d square. Or I have t1 prime is equal to d square by c square minus v square. There is a square here. Now t1 prime is equal to, taking square root, I have here d divided by, let me take c square common outside. So c square, when I take the square root, it will become c times 1 minus v square by c square. We are taking square root, so whole raised to half. So this is the expression for t1 prime. So again, I am going to use binomial expression. So t1 prime is equal to d divided by c times 1 minus v square by c square whole raised to minus half. Again, remember, by binomial expansion. By binomial expansion, just for reference, I am writing it here, 1 plus b, the whole raised to n, will be equal to 1 plus nb plus n into n minus 1 by 2 factorial b square plus etc. And we will be neglecting the higher powers of v square by c square for the same reason we discussed earlier. So we have here, this is equal to d by c times 1 plus b is minus v square by c square. So minus half times minus v square by c square plus etc., which we will neglect, the higher powers of v square by c square. So this is equal to d by c times 1 plus minus half times this plus b square by half is there, so 2c square. So this is the expression. Now this is t1 prime, but the whole time taken by the light to go up and come down is twice t1 prime. So the whole time taken by the light to come up and down, which is t prime, is equal to twice t1 prime, which is 2d by c times 1 plus v square by 2c square. So we have the time taken by light ray to go towards mirror M2 and come back as this expression, and the light takes a time to go up and come down, which is 2d by c times 1 plus v square by 2c square. Now compare these two expressions. Which is bigger one? Okay, definitely this is bigger because the first terms are same and the second term, it is half of this term. So we know that t will be more than this one. So t is more than t prime. So we can find the time difference delta t, which will be equal to t minus t prime. So let me find the time difference. So I have the time difference delta t, which is equal to t minus t prime, which is equal to 2d by c. Let me multiply this expression throughout. So multiplied by 1, it will be 2d by c plus 2d by c is there, and then v square by c square minus 2d by c and minus, because it is minus p square, so minus is applicable for both terms, 2d by c v square by 2c square. So this gets cancelled, 2d by c minus 2d by c. So this is equal to, and in this expression we have 2d v square by c cube common, 2d by v square by c cube common taken out. So this is 1 minus, this will be just half. What is 1 minus half? 1 minus half is just half. So this is equal to dv square by c cube. There was a 2, but because of this half gets cancelled. So the time difference delta t is equal to dv square by c cube. So this is the time difference. Now what is the path difference? Path difference is time difference times the velocity. So this is light traveling, so I can take the velocity of light as c. So we have path difference. Path difference of the light rays is equal to delta t times c, which will be equal to delta t is dv square by c cube multiplied by c. One c gets cancelled, so dv square by c square. So this is the path difference between these two light rays which gets reflected by mirror M2 and M1. Now, because of the interference of these two light rays with the path difference, an interference pattern is observed through the telescope. Now, if the whole apparatus is rotated through 90 degree, the whole apparatus, if rotated through 90 degree, the path difference will become 2d v square by c square. The path difference will become double. Now, if there is a wave having wavelength lambda, and if the path difference between the two waves that interfere, and there is a fringe shift of n, if n fringes get shifted, then the path difference required is n lambda. So you can put the path difference as equal to n lambda, which we got as 2d v square by c square, where n is the number of fringes that get shifted and lambda is the wavelength. During this experiment, Michelson and Morely used wave of wavelength lambda is equal to 5000 angstrom. So they use light having wavelength 5000 angstrom, which is equal to, angstrom means 10 raised to minus 10 meters. So 5 times 10 raised to minus 7 meters. And the distance which they maintain between the plate and the mirror, both mirrors, d was 10 meter. And we know that the velocity of earth is 3 times 10 raised to 4 meter per second, and the velocity of light is 3 times 10 raised to 8 meter per second. Now if we substitute all these values here, we will get n as equal to, we have n is equal to 2d v square divided by lambda c square. So substituting all these values, 2 times 10 times 3 into 10 raised to 4 the whole square divided by 5 times 10 raised to minus 7 times 3 into 10 raised to 8 the whole square. If you calculate this value, you will get it as equal to 0.4. So the expected fringe shift is 0.4. According to Michelson and Morely, their apparatus can measure up to a fringe difference of 0.01. So if there is a fringe shift of 0.4, they could definitely identify that. They could definitely measure. But there was no fringe shift observed. they could not measure any shift in the fringes. They repeated this experiment in different seasons, in different parts of the world, but always with a negative result. They could not find the expected fringe shift. Because of this negative result, there was two important consequences. One is the idea of this all-pervading ether, with respect to which the Earth's motion was intended to measure, was discarded. They ruled out the idea that the whole universe is filled with a hypothetical medium called ether, and the concept that all motions can be measured with respect to that and consider that as an absolute motion. So the idea of absolute motion was ruled out. That was the first consequence, and the second consequence was that we considered light as having a relative velocity with respect to Earth, right? So it was then thought that light will not have a relative velocity. Light will have a constant velocity irrespective of the frame of reference with which it is measured. So these were the two important consequences of Michelson-Morely experiment, and it set the stage for Einstein's special theory of relativity, which could be discussed in the next class. So hope you understand this experiment, and if there is any doubt, you can ask me.